Now we confront this issue that all of us run into almost every day, and that is the death of a battery. We have an electronic device, it's working perfectly, and then all of a sudden it stops. And it stops because the battery is, in quotes, dead. But what does that actually mean quantitatively in terms of electrochemistry? So let's start out with our Gibbs free energy expression. Delta G under non-standard conditions is equal to delta G under standard conditions plus our RT log Q. This is the hill down which these electrons are rolling. When we have a brand new battery, we've got a nice high Gibbs free energy surface from whence those electrons come rolling down. As time goes on, the battery begins to wear out. That delta G begins to decrease, and it continues to decrease. But we also know something else, and that is that delta G is equal to minus NF times the cell voltage. So all this decay in delta G through the course of the life of that battery is directly proportional to the drop in the voltage of that battery. So let's see what that means in terms of unifying all of these ideas that we've had. So we start out with our expression for delta G under non-standard conditions. And then into that we will substitute our expression that Michael Faraday gave us, minus the number of moles times the Faraday constant times the cell voltage. And notice that this expression that Faraday deduced is applicable both under non-standard conditions and under standard conditions. And that means that we can do a direct substitution into our expression for free energy, because delta G, I can stick that in directly. That's minus N times the Faraday constant times the cell voltage under non-standard conditions. I can substitute directly for delta G under standard conditions. That's simply minus N times the Faraday constant times the cell voltage under standard conditions. And then I have a plus RT log Q left over at the end of that equation. That means that I can solve at any time I want for the cell voltage under non-standard conditions. So I want to calculate my cell voltage during the course of the life of that battery. So if I multiply through by minus 1 and divide through by NF, I have a really simple deduction that the cell voltage under non-standard conditions is the cell voltage under standard conditions minus RT over NF times the log of Q. So that means that as we go through the sequence from a brand new battery to an aging battery, remember that Q is equal to the activity of the product times the activity of the other product, D, divided by the activity of the reactant A times the activity of the reactant B raised each to its stoichiometric coefficient. So as life goes on, as the battery is used, more and more of the product builds up. And that means that Q gets larger and larger through the course of the life of that battery. And because of that negative sign in there, at a certain point, that quantity overcomes the cell voltage under standard conditions, and the cell voltage begins to drop, delta G begins to drop, and the battery goes dead. Walter Nernst deduced this simply by putting the Faraday expression delta G is equal to minus N times the Faraday constant times the cell voltage into our expression for delta G under non-standard conditions. And all of a sudden, he was credited with coupling those thermodynamic expressions that then defined the completion of our master diagram.